Cool, so let's talk about L'Hopital's rule. L'Hopital's rule is actually pretty simple at its core, but gets into some kind of funny, complex algebra when you try to evaluate it. So, L'Hopital's rule is limit. So we go back in time to what a limit is. So a limit as x approaches a, or infinity, I guess, but usually a. Yeah. So as x approaches a, we'll usually have a function, so f of x, and we try to figure out what value does it go to as it goes to. So if x is linear, like 2x, as x goes to, I don't know, 5, it's going to approach the value of 10. Because it's just like it's not actually doing anything special. When you have an asymptote, like other little stuff, it'll be like, oh my gosh, you're approaching infinity on a graphic like this. We'll just go to infinity. No, not more. Hopefully, we don't understand that. But you often get scenarios in which you have a function on top of a function. For example, f of x over g of x. And the truth be told, sometimes this can result in some kind of funny scenarios where you try and evaluate the limit, but you keep getting weird things like infinity over infinity. So the limit values to infinity over infinity. You get 0 over 0, or if you have other scenarios where it's an exponential or other weird things, you're going to get stuff like infinity to the power of 0, 1 to the power of infinity, yeah, 0 to the power of 0, 0 to the power of 0, and 0, infinity minus infinity. Infinity minus infinity, 0 times infinity. I think that's how I went to that. This one. 1 to the power of infinity, infinity to the power of 0, 0 to the power of 0, infinity minus infinity, 0 times infinity. Those two guys. Okay. So sometimes when you're evaluating a limit as x goes to a value, you end up with things like this. I like to call these like the rad forms. But really they're just like mathematical paradoxes, which means we have to treat them with this special term. They're called indeterminate forms. That's what the name of these things is. Indeterminates. Because you can't actually value them. For example, if you divide infinity by infinity, your intuition will tell you, oh, the thing divided by itself is going to equal 1. The problem is, the concept of infinity is infinity. It's not supposed to be limited. So, if you divide infinity by infinity, you have a paradox, because what was once infinite is now finite. Same with 0 divided by 0. You would think that, oh, same number divided by same number, or number divided by same number gives 1, but the idea of 0 is we have 0, and you cannot make 1 out of nothing. Same goes for these. Infinity to the power of 0, you would think would make it 1, but actually that kind of negates knowing ones what infinity is. 1 to the power of infinity, well, infinity is supposed to be infinite, but it stays stuck at 1. Infinity to the power of, or 0 to the power of 0, same problem here. You would think it would be 1, but it's not. Infinity minus infinity, same problem, and of course 0 times infinity. Because all of these negate values. Now, what are some you would think would be indeterminates that actually aren't? One is infinity plus infinity, which is still infinity. Like the idea of indescribably large plus indescribably large is still indescribably large, so you don't actually have a problem. And what's the one? I think there's another one. 0 times 0 is not the thing. Oh yeah, and stuff like infinity times 2, or infinity minus 1, or infinity plus 3, these are not determinants. These are all determinate, and we don't care about them. So you can just kind of see them there, like whatever. Because infinity minus 1 is still infinity. But infinity minus infinity, that's not a problem. So all these are indeterminates. But you'll notice that I kind of grouped them into two parts. That's because there are two different types. There are type 1 and type 2, as one calculus purpose. Type 2 is a special case, and type 1 are only favorites. Type 1 are useful because this is what you can evaluate. We haven't actually touched multiples really yet. This is just kind of some explanation of what we're getting into. These are what we can mess with. These are what we encounter. We have to convert into type 1 with a algebra so we can evaluate it. So what is L'Hopital's rule? L'Hopital's rule is just a rule, just like the power rule or the quotient rule, that lets us evaluate the limit, in which case the limit of f approaches something, and then the limit of g approaches the same other thing. And whatever relationship f and g have is going to match this. Limit f and limit g, where it ends up looking like this. So you can also have like f of x to g of x, which would end up with you getting something like, oh my gosh, f of x goes to, I don't know, 1, but g of x goes to infinity, which means we have an indeterminate on our hands. Same for 0 times infinity. Let's say it was f of x times g of x. Limit as x approaches a, f of x goes to 0 and g of x goes to infinity. Boom, we have an indeterminate. And we have a problem. So, L'Hopital's rule is the way that we get around this. So, I'm just going to write the indeterminates over here so you can see. Infinity over infinity, 0 over 0, times 2, infinity, 0 over 0, infinity is infinity. 0 times infinity, and 0 times 0. There's 7 indeterminates. So what we do, L'Hopital's form essentially says when you run into a scenario where you end up with this, specifically these, then we get, which is a f of x over g of x. There's a relationship between that as well. Actually, it has to be this. Is equal to f prime x g prime x. That's as simple as it is. The rule itself, the applications are a bit more complex. But in essence, it's this. When you end up with a limit where f and g approach those values, you can just take the derivative of both of them like separately. It's not even like a quotient rule or something. It's just you take the derivative at the top and put in the numerator, derivative at the bottom, put in the denominator, and then evaluate the limit as is. It's really useful for just going down tiers until you finally get to where one of them is equal to something else, or the limit of one of them is equal to something else. So if g of x limit and g of x approached infinity, and then in this one it approaches 1, like the derivative approaches 1 as good as that value, boom, you can just plug in a for the f, and then you have the value of your limit. So that's what it is. It gets harder when you end up with one of these in the problem, and what you're going to have to do is find different tactics to convert type 2 into type 1. And then you can apply L'Hopital's rule to it. And yeah, so that's the idea of it. That's the rule, and kind of how you can use it. In the next video, let's get into some examples, and all will be well.